about discovering abstract topics that occur in a collection of documents. And to illustrate that, we see in this Wikipedia page, you have all a bunch of text, and we want to be able to transform this to the most important words in that text. So in this example, we see topic, document, words, text, and model, and that's processed from the Wikipedia text. So basically, I wanted to, how can we build this type of functionality in Python where the input is just a document and then the output is just the topics associated with that. So there's a library called GenSim, which is a topic modeling library that has lots of different cool abilities and APIs and just ways to interact with text. But to actually do that simple step of creating a topic model and outputting those words consists of going through 18, 20 different steps to kind of just build a pipeline to do that. So it's not really beginner friendly. There are a lot of steps involved, and it's really not an easy process. So one of my guiding principles is how can we invent and simplify the process of topic modeling so it's more accessible to developers alike. So I designed this open source platform called Topic Blob, which is basically a simple API that takes in text and you get topics out of it. It was modeled off another popular library called Text Blob, which you just take text and it gives you a sentiment analysis. So similar type of thinking here. You have raw text as the input, and then you get topic text as the output. And here's an example of the text. A lot of random text paragraphs. You make an array with those text paragraphs. Topic blob, you just pass in the documents, how many topics and words, and then it does a bunch of analysis, and then you get each of the topics displayed right then and there. This is a simple API that just encapsulates that entire process GenSim is doing behind the scenes. And I actually open source built this with the community during Hacktoberfest of 2020. So about 8 different community members were able to come in and take issues, close these issues, work on them. And it was great just having other individuals come in and build the application besides me. But when you're building a community-based application, you need to have well-scoped issues so people can easily jump in and get in and start building. One of the biggest barriers to entries I see in open source projects is no really clear path on how to start and what I can do as an individual contributor. With this Hacktoberfest, there are people from all over the world participating, and I don't know, there's no really sense of like what they've done before. So just setting them up for success is a really important thing for getting community involvement. So I always start with what the task is, why do we want to do the task, and then how somebody can get started. And that definition of done, by providing that template, it really allowed those individuals to easily contribute to the project. Then, so a quick little demo. One of the things was actually make a Streamlit application with a topic blog. And the idea is basically we have a bunch of Wikipedia pages. We can see all the actual text topics that are extracted from each of those. You can find similar pages. So topic blog does other text analysis tasks, such as finding similar pages based on the topics, doing rank search. So I did Python here, did a rank search, find things that have the Python, but Python's the only one in what examples I put. Search for specific topics. So if I search Meta, Facebook company comes up. So it really just gives you an opportunity to do a lot of text processing tasks around topic modeling. And it's open source. It's a GitHub. You can post it afterwards, and you can install it with pip install topic blob. So it's really cool to build this with the community. So I had 8 different contributors build this. And this, I really never saw anything else that really encapsulated the topic modeling API. Using GenSim was great, but there's so many steps involved to doing it. It wasn't very easy and user-friendly. So this was really the motivation to invent and simplify that process of topic modeling and have a nice API that allows anybody to use that. And that's all my talk. Thank you.
Thank you so much, Banjo, for the talk. And I guess we can have time for a question, maybe in the chat, if anyone has any. But otherwise, If not, we can switch gears to the second talk with Thomas. And as you get ready, Thomas, just
Hello, do you hear me?
yeah.
Okay, great. And are you seeing my screen?
Yes.
Okay, great. Can I get started?
Yes.
Okay, hello everybody. It's a pleasure to be here giving this lightning talk for all of you. I'm Tomas Capretto. I am from Argentina. And today I'm going to talk about Bambi, which is a new library for Bayesian modeling in Python. So let's get started by reviewing the outline of this talk. So I'm going to describe what is Bambi and the main features around Bambi. I'm going to give you some examples where I'm using Bambi to do Bayesian modeling. Then we have some short time for conclusions. And I'd like to tell you how you can get involved with the project. So Bambi stands for Bayesian Model Building Interface. And it is an interface because it is built on top of other libraries like PyMC and RVs. So every time you create a model in Bambi, Bambi under the hood is creating a model in PyMC. And we use RVs because of the data structures that it provides, and many plotting functions to analyze prior and posterior distributions, for example. And now let's review some of the main features in Bambi. Bambi supports generalized linear mixed models. These models are also known as multi-level models or hierarchical models, especially in the Bayesian literature. Bambi has a short and simple model specification syntax. This model formulation with a model formula is inspired on the R programming language and the model formulas that you can use there. And the result is that you can write your models with less code, which results in save time. Bambi supports both numerical and categorical predictors, and it doesn't ask the users to perform any complicated data preparation steps. These steps are usually associated with errors, so it saves you debugging time. Bambi doesn't enforce you to explicitly pass your prior distributions. So this is good for iterative model building, but Bambi also allows you to pass your priors when you have the model that you want to use, and it's recommended that once you have that model, you use your priors. And finally, if you are familiar with how PyMC works and you feel comfortable working with PyMC, Bambi still gives you access to the underlying PyMC model. So let's get started with a first example. In this example, we are interested in estimating the vote probability. We are going to use some survey data coming from the American National Election Studies, and this data can be loaded with Bambi very easily with the load data function. And we can see we have 3 columns: vote, which is our variable of interest, the response variable, the age of the respondent, and the party identification of the respondent. Oh, this was data collected before the 2016 election. So, and we are going to build a model to estimate the probability of voting for Clinton. So let's go to the next slide. And something very important is that all the models in Bambi are created with a model class, and it has 2 mandatory arguments: the model formula that we can see here, and the data, which is a pandas data frame that Bambi is going to use to look for the variables that we are passing in the model formula. Here we are also using a 3rd optional argument to tell Bambi that we are analyzing a binary variable. And Bambi is going to interpret this as a binary variable because we are saying, okay, my response is vote, but I want you to model the probability that vote is equal to Clinton. This means that we are not using an intercept in the model. This means that we are using the party identification as the predictor. And this means that we are using the interaction between the party identification and the age. When we print the Bambi model, we have some important information, like, for example, the prior distributions, which is something that we didn't specify when creating the model. And so here we can see, for example, that Bambi has chosen normal distributions centered at 0, which is a pretty common choice. And it has estimated, sorry, I hear something. Oh, okay.
It's fine. Yeah.
It's fine, yes. And it has estimated the standard deviation using a method that we have implemented for this purpose. Then once we specify the model, it's time to start the fitting process. And in Bambi, it's as easy as saying model.fit. And under the hood, it is calling the sampler from PyMC. It's giving us some good information, confirming that we are modeling the probability that we want to model. All the other messages are thanks to the PyMC sampler, which tells, for example, that this fitting process took 11 cycles. The result of this fitting process is an object of class inference data that we are going to use to analyze the posterior results. So we specified the model, we fitted the model. Now, for example, let's suppose we have data about other subjects that we didn't use in the training stage, but we want to know what's their probability of voting for Clinton. So let's say we have these two observations. They are both from the independent party, and they are aged 20 and 60. So all we need to obtain these Bayesian predictions is to use the predict method. We pass the inference data object that the fitting process returned, and we pass the new data frame. This is going to update this inference data object, and we can easily create a chart like this one, which, for example, tells that the probability of voting for Clinton is higher for the youngest person, but however, we have more uncertainty about this estimation because the distribution is wider. We have distributions because we are using Bayesian inference, so these are posterior distributions. And if you have a little more time and more creativity, you can create this, which is more informative. So instead of having only 2 observations, you can create a bunch of observations and create a plot. Use the same predict method and create a plot like this one to analyze the association between age and probability of voting for Clinton for the different party identifications. And this is one of the good things about Bayesian inference, because we not only see the estimations, like, for example, that Democrats always have high probability of voting for Clinton, but we also have an idea of the uncertainty about the estimations. So we are more certain about these estimations that are, for example, these other estimations that are highly variable. And so, and as I said, Bambi is an interface to PyMC, and it writes PyMC code under the hood. And so this is how the PyMC code for the same model looks like. As you can see, this is much more expressive. It may be more clearer for some people, but it's also much more code. And so you can make more mistakes here. Then we have another example that I'm not going to cover in such a detail. So this example is about a psychological study where people were deprived from sleep, and they wanted to study reaction times after several days of sleep deprivation. So this is a plot of the data. We have one panel for each subject. We have the days here and the reaction times here. We are seeing that the reaction times increase as people are more deprived from sleep. So we are going to estimate a linear model here, but this linear model is going to be a hierarchical model because we want to include an intercept and a slope common to all the subjects, but we also want to model the deviations of each subject from this global pattern. So we are going to include intercepts and slope specific to the subjects. Doing this in Bambi is as easy as adding this type of term, this it's just saying that we want a daisy slope for each subject, and implicitly it is saying that we also want an intercept. And you can see that this summary is much longer now because we have many more terms. And again, fitting the model is about using the fit method. So we can, to have an idea of if subjects differ, we can see the posteriors for the subject-specific intercepts and the posteriors for the subject-specific slopes. And so the first thing that we note, comparing the intercepts, is that subjects differ in their initial reaction times. Some of them are below the mean, some of them are above the mean, but they also differ in how much they are affected by the sleep deprivation. Some of them are more affected, so their slope is larger, and some of them are less affected, so the slope is not that large. And here we can, from that information in the posterior, using some RVs and Matplotlib code, we can obtain a plot like this, where we have the estimated linear regression for each subject, and the bands indicate a credibility interval, a Bayesian credibility interval. And this is the PyMC version of the same model. Again, it's a much longer piece of code. It's much more expressive. It's clear about what's going on if you know what you're doing. But we have, I don't know, 20 lines of code when we had here this line of code. So, conclusions. Bambi provides a simple syntax. Since it's simple and shorter, it is less error prone. It is still flexible. You can use your own priors. You can create your own family of models. I haven't covered that here, but feel free to have a look at the documentation. It is not as flexible as PyMC, of course. It is going to be familiar to you if you have experience with R because of the formula, of the model formula. And it reduces, more importantly, it reduces the cognitive load. So you don't have to think that much about how to write your model. You can take that time to think about your problem. And finally, I want to tell you how you can get involved with this project. So Bambi is hosted and developed on GitHub. If you are interested about the library, please contribute with anything you want. We have a documentation webpage, and you can reach out any of the core developers on Twitter. If you use Twitter, you can find Osvaldo Martin, and you can find me on Twitter. And we are very open to suggestions, ideas, questions, or anything that the community has to say about the project. And this is it.
Thank you very much, Thomas.
Thank you.
Awesome meme. Just before we go to the next talk, we have a question from Ryan. Are there any plans to provide operator overloads so that users don't have to specify models using strings? And I'd like to ask you to answer it in 1 minute or less. That's my challenge to you. So,
but to that, you should know how to. No. So in R, you don't use a string because of how R evaluates the arguments of functions. So you can pass something that doesn't look like as a string because it uses lazy evaluation. But in Python, you are forced to use a string. But if your question doesn't go up, it's not about that point. So we are going to keep using this string because it was what it makes difference PyMC from Bambi. Yes, yes.
Thank you so much, Thomas. I think you answered the question perfectly.
Okay.
And before we move to Zachary, I was challenged by the conference chair to throw in some jokes. I mean, I have deep learning jokes, but I cannot explain it. So I guess we can move to the next talk with Zachary about automatic pattern-based data catalogs. Zachary, are you here with us? Or?
I am. Yep. Can you hear me?
Yeah.
Wonderful. Hello, everyone. Thanks for coming. These lightning talks. My name is Zachary Blackwood, and I am on the data science infrastructure team at DTN. We're a global leader in agriculture and weather and energy And I want to talk to you about a problem that we had with the data science team in terms of cataloging our data and how we solved that through an existing library and also through adding on to it with a new library called Intake Pattern Catalog, or affectionately shortened to Pattern Cat, hence our icon. So really the reason behind all this is we'd face this problem again and again on the data science team, that we have a lot of data. We're very much a data-driven company. We've got access to a lot of data. It's just a matter of where it is, how do you get it, and every time a new project came along, or there was a quarterly hackathon and we had some great idea, it was typically about 80% of the time was spent finding the data, figuring out how to access it, figuring out what we need to load it, and so we had this. We had this issue, and one of the things we did to solve it was to create a data catalog to make our what might be generously called a data lake into something that's actually more usable and accessible. So the first part of our solution was finding and using this wonderful library called Intake. So Intake is a tool for creating data catalogs, where you write down the catalog specification in YAML files, and then it provides, so with each entry in your data catalog, you specify where it is, and also what kind of driver you need to access it. So whether it's a CSV, or you're going to load it with a Parquet reader, or it's SQL. And not only does it then give you a way to see what data is there, but also gives you a consistent Python API for accessing the data. And this was really a game changer for us, for getting access to the data and for making the process much smoother. And so the workflow for finding new data and getting access is used to be something like this. I got to look in this certain folder, or look in this certain location, find the file that I'm looking for, use this specific tool to get the data, and then do some other filtering and cleaning and to get the actual data that I want in the format that I want it. And this was this was almost always the case. There was always this multi-step process that was always different depending on where the data was and what format it was in. And once we started using Intake, the steps call this Python API, catalog.category.dataset.read, where category and dataset are it. And it really is that easy. And this was a huge game changer for us. It gives you access to this data as a data frame, or as a dash data, as a pandas data frame, or a dash data frame, or other various formats. And this alone was a big game changer in terms of not only seeing what data was there, but also having access, having easy access to it without having to worry about what it was under the hood. But there was a particular use case that wasn't entirely solved with this. We have a lot of cases where we have a lot of data in S3 and some on disk somewhere, and it would often be stored in a structure like this, where you have a certain bucket, a certain folder, maybe a customer name and a date and a version. And so we had these cases where, look, here's a lot of data. It's really the same kind of data, maybe even have the same, may have the same structure and everything, the same format. But we didn't want to reference this by creating a whole bunch of separate entries in our YAML catalogs. I wanted to have a single entry that contained this, that would allow us to reference an individual one of these. So there was already functionality for if your data was split into multiple files, but these really are separate data sets. And we wanted to be able to create a single entry that allowed us to access multiple of these and pull them out as separate data frames. So that's why we created this thing, what we call Intake Pattern Catalog. Is installable now with Conda. It's on Conda Forge. You can install it with pip. And the way of using it is very similar to what you would do with a regular intake catalog. The differences would be that you specify this pattern cat is the name of the driver. And then you specify, instead of giving a hard URL either a local URL or something on S3, for example, you give it with this f-string style patterns. And so you say here, the syntax or the structure of my data is always going to be in something bucket folder, some customer name, some date with this format, and some version number. And then underneath for each individual entry, I'm going to use the Parquet, driver underneath the hood. And so this allowed us to describe this whole group of files with a single entry in our intake catalogs. And then to access an individual entry, you can hear this is for example, this customer sales catalog entry, which is itself a catalog. It's a catalog of all the different Parquet files, for example. If you list it, you can see all the different entries that are there. And then if you want to get a particular entry, you can just pass with keyword arguments, say the customer name and the date or whatever the parameters are in the pattern that you described, and then doing .read or .to-dask or something like that to get it in the format that you wanted out. And so this allowed us to compactly describe things that are a whole bunch of files, even a bunch of files that is growing over time as we add new data and still have a single entry. So we're using this extensively at DTN. We're using it both in experimental projects and also in production. Here's some of the ways that we're using it. We have a lot of things where we have similar kinds of files, but there's different customer names in the path, or we use different processing steps, and we have a version number in the file name, or we do a lot with weather predictions, and so we'll often have weather that has a date in various formats, and we even use it to get our models or the model data or the predictions that have maybe the model version in the path name. And so all of these things are now much easier now that we have this way of building on top of intake. So some of the takeaways are that the things that I've learned and the team of us that's worked on this has learned is that intake is a really useful tool. If you have this situation where you have data in lots of places and you don't yet have a way of creating a data catalog, highly recommend using the intake library. The intake library was built from the very beginning to be pluggable. So it was built with instructions on creating plugins, and there's many community created plugins out there now. This particular one, even though it's a fairly different behavior in that a single entry represents a whole catalog, because the plugin based system really made it very approachable and doable to create it. And it's the whole code base is less than 300 lines of Python code. And then this was actually our company's first open source project, and the experience of getting it on PyPI and then getting it automatically released on Conda Forge was much easier than at least I expected for my first experience with it. So if that's something you've never done, it's very approachable, and there's lots of community help, and there's lots of nice bots that will help with the process of auto releasing new ones. So if you have data catalog issues, highly recommend you use intake. If you want a Python API for accessing your data, take a look at intake pattern catalog if you think it'll solve a problem that you might have, or create your own intake plugin if there's some use case that you don't see there yet.
Thanks a lot, Zach. Thanks a lot, Zach. We have a question from Mark. He's asking, can you have multiple patterns per entry, for example, to cover the case for different date formats?
That is not yet supported, but no. So we only allow a single pattern. So you have to, yeah, that is a limitation. You would have to have a separate entry for a given entry.
Right.
Oh,
thanks a lot, Zach. Do we have Ryan with MyGrad?
Yep.
All right. I tried to think of jokes between the talks, but the one I came up with wasn't statistically significant. So let's move on to the next one.
I dig it. I was gonna say my talk is gonna be a joke in and of itself, so we should be good. Can everyone see my slides and hear me? Hopefully.
Yeah.
All right. Hey everyone, I'm Ryan Soklaski, and I want to present to you MyGrad, which is a library that adds drop-in automatic differentiation to NumPy. So in this lightning talk, I will describe what automatic differentiation even is, what I mean by drop-in, how MyGrad pulls this off, and I'll compare and contrast MyGrad with JAX, which is another NumPy-centric auto differentiation library. And then I'll talk a little bit about why I think this community should care about MyGrad, or why they might care about MyGrad. Okay, so what is automatic differentiation? If I have a number that in my code I represent as a MyGrad tensor, I can pass that to any MyGrad or NumPy math function and get out some output, which will be represented by a MyGrad tensor. Because this is a MyGrad tensor, it has a method called backward that tells MyGrad to compute all of the derivatives of that function with respect to the input. So we get the derivative of the function evaluated at that specific value, x naught. And this is returned as a NumPy array. So a lot of you who have done machine learning have probably encountered automatic differentiation via PyTorch, JAX, TensorFlow. This is like a totally essential technology that undergirds the deep learning revolution and gradient-based learning. So let's see what this looks like in actual code. I make a MyGrad tensor. This is just like a NumPy array. I can pass that MyGrad tensor directly to a NumPy function. And this isn't like some special version of NumPy that MyGrad provides. This is just vanilla NumPy, numpy.sum. The return is a tensor, so I can call backward on it. And that tells MyGrad to compute the derivatives of f with respect to x at that input. Okay, so that's just to make sure we're all on the same page of what this would look like to use in our code. Now, what do I mean by drop-in in terms of drop-in automatic differentiation? So we have typical workflow of using NumPy code is we have some code using NumPy, and we put an array into that code, and we get out usually another NumPy array. Well, I can take that exact same code, whether you wrote it or I wrote it, or it was provided to us by scikit-learn, and I can instead pass a MyGrad tensor into it. That's what I mean by drop-in. And what will come out is a MyGrad tensor. But that MyGrad tensor will know how to take the derivative of the code that we were using. Again, whether or not you had written the code or I did, or if it was some functionality provided by scikit-learn or some other NumPy-based library. So how does it do this? Well, the MyGrad's tensor has two functions that implement a protocol that's actually provided by NumPy itself that allows you to override NumPy's ufuncs or functions. So when I call numpy.einsum on a MyGrad tensor, NumPy actually sees that I have this function override, and I'm saying, hey, NumPy, I actually have my own version of einsum that I want to use. Please use that instead. But the end user doesn't know it. The end user just calls NumPy's version of it on the tensor. Doesn't JAX do this already? Well, JAX doesn't provide drop-in automatic differentiation. It provides swap-out automatic differentiation. So in order to use JAX's NumPy code to add autodiff, you need to write your NumPy code using JAX's NumPy, not using vanilla NumPy. So if someone else, some third-party library, already wrote their code with NumPy, you can't go and swap out their NumPy with JAX's NumPy. So you can't simply drop a JAX array into third-party NumPy code, is what I'm saying. And also, JAX has limited support for NumPy. You can't do in-place operations, for example. Is MyGrad, okay, you might be asking yourself, is MyGrad bad? Like, is this actually good? Is this just going to be some dude's little baby repo and he implemented derivatives for multiply and add and cosine? No, it's pretty good. I've been working on this for 4 years. It's been too much. You should take a look at the source code sometime. It's a bit much. It's lightweight. Its only dependency is NumPy. So if you already have NumPy installed, you do pip install MyGrad, all you're going to get is MyGrad. It supports broadcasting, in-place operations, memory sharing views with parity among the actual gradients. So the gradients share memory as well. first-class support for ufuncs, so you can use where masks, out targets to write to specific parts of tensors. Gosh darn robust support for einsum, which is just like the killer linear algebra operation. You can even do views of diagonals. That took me an entire weekend. It's fully type annotated, super duper tested using hypothesis library. I became a developer on the hypothesis testing library because of my work on MyGrad. And it has pretty solid docs. Like we have examples for all of our code and stuff like that. And we even have some neural network operations. You can do n-dimensional convolutions, pooling layers, batch norms. We even have a group. So it's a pretty serious library. You might also ask, I already use JAX. Should I use MyGrad instead? Oh my goodness, no, absolutely not. MyGrad is not meant to compete with JAX. MyGrad does not have higher order derivatives, JIT capabilities, parallelization, any funding, a large user base, or a team of super smart, super competent paid developers from like Google Brain. No, we do not have those things. So why should the NumFOCUS community care about MyGrad then? First of all, it's super accessible. It's maybe the easiest way to compute derivatives within the NumPy ecosystem. It's just NumPy, but then you call that backward at the end of it and you get the derivatives. It's awesome for teaching. I teach an outreach course through MIT to high school students about machine learning, and all we use is MyGrad. It doesn't have the sharp edges of trying to install PyTorch across different operating systems or dealing with, I mean, JAX can't even be installed on Windows without hacks. The documentation is more user-friendly. And if students want to know how to use MyGrad, I just tell them, or I just teach them how to use NumPy, which will teach them how to use pandas, how to use Xarray, how to use CuPy, right? NumPy is at the core of this entire ecosystem. So just learn how to use that. It could add autodiff to CuPy, Xarray, Dask, sparse array. There's this emerging array API standard that Ralph Gommers is spearheading. And I designed MyGrad really carefully to have parity with NumPy. So you could use a MyGrad tensor under the hood to add autodiff to these other really popular and really powerful libraries. And the last reason is I don't really plan to work on this anymore unless people find the above useful. And I don't mean that in like a negative way. And I don't want your pity. I'm just saying I'm happy with MyGrad as is. It's really great for my personal use cases in teaching. But if people look at the above and say, hey, I really want autodiff for sparse array, then please reach out to me. I would love to have people extend this project and continue working on it. But just in terms of like me by myself with no one other than my students using it, I'm happy with it. It is what it is. Finally, it's not MyGrad, it's our grad. I always have to explain this to my students. I didn't name it being like it's my Ryan Soklaski's grad. It's supposed to be relative to the actual user. Yeah, and so MyGrad is on GitHub, on PyP. You can find me at RSOKL on GitHub and Twitter. And I'm giving another talk at 5 o'clock. So if you like my energy, and if you like the style of this talk, please come learn about Hydrozen, which is a pretty serious library that I'm working on. Thanks, everyone.
Thanks, Ryan. Awesome. So can you maybe type in the chat how people can find you on GitHub?
Yep, RSOKL for GitHub and Twitter.
Awesome. Thanks a lot. With that, we can move to the talk with the Xiuwen Tu, and excuse me if I didn't pronounce it well. Do we have you here? Yeah. All right.
I'm here. So,
okay, fantastic. You can share the presentation and
okay, let me share my screen. And I can get to. Oh, how come it's so small? Okay, now it's full screen. Hello, everyone. My name is Xiuwen Tu. I'm here to talk about a very simple exercise, approximating pi with fractions using Python. So here's the outline of my talk. In the interest of time, I'll just skip through. So here's the motivation. Pi is a really interesting number. And apparently there is a competition worldwide and throughout history to see who competes the most number of digits, right? So this graph was was generated back in 2012 on Wikipedia, uploaded there. And then I added 3 later events just in the past, say, 2.5 years. So seeing those interests, I was also learning Python, okay, still learning. So I asked myself, what are good fractional approximations of pi? And what are Python features that are useful, say, if I investigated this? And I'm not going to hold it to the end. So here are the answers I found. Basically, the ratio 355 divided by 113 is a very good approximation with 85 ppb and also quite memorable. And the next is 22/7 with a 402 ppm accuracy. It's also quite familiar, I think, to many people. And in the course of the learning, I found the decimal and the fraction and even int to be very useful. So first I loaded the decimal module and the fractions module. Both are in built-in modules. Then I immediately set the precision to 52 decimal points in the context. Then I found the first 50 digits of pi from this from this Wikipedia page, and I passed that to the decimal constructor. And I was happy to see that it appeared to retain all the 50 digits. To start with, I look at math.py and numpy.py. They are equal, and their accuracy is roughly 4e minus 17. And this 50 digits of pi is roughly 3 times of that. So here's the main part of this. It really is as simple. So this talk is more like a joke to any of the jokes you heard so far. I passed the decimal pi with 50 digits to fraction, and I used the method limit denominator to ask for fraction approximations to this decimal number, right? And I pass in this max denominator with larger and larger numbers, and then I calculated the error. I need to use the decimal representation of these numbers to get the relative error, and then I collect the denominator and error and print out the results here. So what we see is that as the max denominator is allowed to double going down, right? Both the denominator and the numerator of the fraction approximation indeed get much bigger, and the relative error also became much smaller. So here's the rest of the printout. As the max denominator gets close to the power of 90, we maxed out the precision in there. I mean, the 50 digits of the pi and also the 52 digits of precision I set in the context. So here is a plot of the relative error against the limit denominator, both in log scale. And I need to multiply those with the negative relative error with the decimal -1 to have them show up in the log scale. And one thing we see is that a few fractional approximations, they are good over a range of limit denominators, meaning they are good, right? So I pointed out the 4 obvious ones here, and to my head, only the first 2 are memorable. And by the way, this ratio of 355 divided by 113, so it was known historically as Zu's ratio. It was discovered by a mathematician in 5th century in China. So it was an interesting one in there. There is also the so-called continued fraction representation of pi. So this formula is taken from Wikipedia. What we see is that it has a very regular structure, and these series of numbers essentially together with the structure essentially defines this continued fraction, right? So the Wikipedia page says truncating it should give us these numbers. So I did this manually with the first 4 terms to confirm that I knew how to do it. then I wrote a small recursive function to calculate that. So I found these first 20 terms from this web page. And then after correcting this function, it worked out these terms. And indeed, the 22/7 and the 355/113 are here. And the first couple of, a dozen of terms really matched what's listed in that Wikipedia page as well. So here's one way of looking at why is this ratio so good. So in this simple continued fraction representation, this number 292 is quite large, meaning that dropping this only creates a small error in the result. And indeed, this ratio can be obtained by retaining only the first few terms and dropping all the 292 and beyond. So here's the takeaway of my talk. It's a very simple one. A very good fraction approximation is this ratio, 355 divided by 113. And one trick to memorize this is the inverse of that is 113355 with a divide sign right in the middle. Right? It has impressive accuracy. So the runner-up is our more familiar 22 divided by 7 with 402 ppm. And in the course of working out this exercise, I learned about decimal fraction and even int with the number not maxing out at, say, int 64 limit. I was also happily delighted. So finally, here's a GitHub link. Okay, thank you.
Thanks a lot, Xiuwen. And we can now move to the talk afterwards with Usman with the need to, or for modular data science solutions. Do we have Usman? Yes.
Hello.
Can you hear
me okay?
Yeah.
Yeah, I can hear you.
Okay. All right. So as you're setting up your presentation, can you, Xiuwen, can you stop sharing your screen?
How do I do that? Can you take the control away or stop share? I found it. Sorry.
Okay. Okay, great.
Okay, I'm just gonna go ahead and share my screen.
All right. In the meantime, I'll try to throw a pun. There are two kinds of data scientists. Like first ones, the ones who can interpolate or extrapolate from incomplete data. And now we can start your talk. Usman.
Perfect. So hi everyone, my name is Usman Kamran, and I'll be talking to you about the need for modular data science solutions. And let's get this rolling. So I'm part of now Vertical Group. It's a group that focuses on delivering data science solutions to a number of industries and use cases. And it's a parent company of a company that I've been involved in the past 3 years or so, called Integra. And Integra really focuses on delivering data-driven applications and data-driven insights to use cases within the oil and gas industry. My role within this sphere is as the cloud solutions architect and the technical lead of the Digital Hub project. Digital Hub is a cloud-native, scalable data science platform that is ready to be used. I encourage everyone to take a look into it. This talk is really focusing on some of the things that I've learned over the last 3 or 4 years while I've been transforming data science experiments into data science projects, and then ultimately data-driven applications for enterprise use cases. And some of what I've learned is the importance of modularity within this entire sphere. So a lot of the time, what happens when it comes to data science experiments and data science teams is that they exist within their own independent silo, where the goal is just value generation from the data that's available to you. And a lot of the times this makes sense because most often when data is provided for data science teams, it's unclear as to whether they will be able to generate insight from it or not. There's a lot of time that goes into data parsing and data cleaning, and before having a good idea of what the data contains and what the data entails. it's difficult to identify whether or not you'll be able to generate value. But in restricting data scientists to their own independent silo, what ends up happening is long, messy Jupyter notebooks that, while ultimately functional, are not product ready at all. And the goal when it comes to the scope being an enterprise ready application is really to have product ready code or code that can be easily parlayed into a backend API or a backend of an application once this process is complete. So in order to bridge that gap, it's important for development teams that play a role in the data science experimentation phase, just so you can have and maintain consistent standards when it comes to formatting code and ensuring that the code that you have can be parlayed into a backend ready application. And oftentimes this saves months and months of time when it comes to reworking code into the back end of an enterprise grade application. So even within an evolving scope, the application comes along with you. And I guess when it comes to breaking things down into its own constituent components, that's really where modularization comes in, because the key goal of modularization is to break everything down into constituent components that can be reused and that can scale independently. So the smallest, most core components that I'm sure we're all familiar with are functions. Functions are your friends. Use them often, use them well, and document them as much as possible. Because these functions can be, it might seem trivial, but these functions can be easily parlayed into any given application, regardless of the use case itself. They're the smallest constituent component of an application that can be easily transferable. So functions are your friends, use them often. The second thing is parallelism and concurrency. We're well past the days of single core engines and single threading. And it's important for data scientists and developers both to be cognizant of this and really utilize the compute available to you in the multi-core world that we live in. So you can have, if you can have tasks being interleaved into multiple cores and multiple processes, you should do so. And the way to do so is by using Spark. Spark has a wide variety of use cases, specifically for MapReduce functions. Dask is another library that exists, or even Python's own native multiprocessing library. What this also allows for is later on, once you're utilizing compute at a much larger scale in an enterprise-ready application, you can utilize a far greater amount of compute available to you, and it also makes data processing a lot more efficient as well. The last thing is think about infrastructure early. So there are a number of different benefits of doing so. When you think about the infrastructure early, you can, as a data scientist, you can, if you can containerize your code and have it ready to deploy on a scalable infrastructure, you already have an idea of the financial overhead required to run your application if it's going to be translated into an application of any sort. And this can help inform the financial stakeholders at play as to what will be required when it comes to this level of transformation, which is key in decision-making and the business value that this piece of work can ultimately generate. So there's the financial component of it. The second is the value that a data scientist can deliver from testing their code on an increasing amount of data with a scalable infrastructure. So Dockerizing, containerizing your code, and having that modular component at play gives you the ability to test with an increasing data set and further test your ideas. Yeah, so those are my little keys to success when it comes to transformation of data science solutions. And I hope you found this helpful. Thank you.
Thank you very much, Usman. I can, at least for the lessons that you've shared, at least relate to that half of my time is spent cleaning the data and the other half is complaining about cleaning the data. So with that, we can move to the next presentation with Ardo. Do we have Ardo here? And Usman, you can now stop sharing your screen. What about Jason? Oh, Ardo, are you here?
Yep, I'm here.
Oh, right. Okay. All right. You can go ahead.
All right. Thank you. Just get started here. All right. Excited to be here. Appreciate everybody who's turned up on a Saturday. I'm Ardo, and I'm a data scientist at Clio, and we are a software as a service company operating in the kind of legal tech field. And I'm going to give you a little bit of information about how to use survival analysis to study customer behavior. So if you go and Google survival analysis, what you usually most likely end up with like figures like this from clinical trials or medical papers. And it's a fair question to ask, like, what do you do with survival analysis in a software company? And it turns out like we can do quite a bit. So I'll cover two examples. The first would be churn. So churn is when we lose our existing paying customers, so we lose revenue. And obviously that's not something the company wants to see. So it's definitely something you want to keep an eye on and how those numbers and metrics are. And the standard approach is pretty straightforward. You look at how many accounts you have at the start of some time period, usually like a month or so. And then you look at the end of the time period and how many accounts you lost. And the churn rate is just the ratio of those. This is fine if you want to just kind of have a really sort of overall view, but sometimes we want to kind of zoom in a little bit more. So for example, let's say we have a hunch that there's something wrong with our onboarding process and we're losing a lot of customers like in the early stage of their customer journey. So we want to like really understand like what's happening in like the first 30 days after the customer signs up. And to kind of get a little bit more quantitative about this, I'm going to generate a data set for 1 month. So for each day in a month, we'll have 1,000 new accounts that sign up. And then each of those accounts after they have signed up have a 2% probability of churning on any day. So it's not dependent on like how long they've been a client, is 2% flat every day. So if we can visualize this data and like we have time going from left to right here, and each of these lines represents one account or one customer. And this is like the data we would usually have. Like if we just pull data from our database, this is what we don't know anything about how we generated it. And here, like the left side of the line shows when the customer signs up. And for the red lines, the end of the line shows where they churned. For the blue lines, they didn't churn in this time period that we're looking at. So we just know that, well, there still are customers at the end of the time period we're looking at. So if we now use the sort of simple approach and calculate, okay, out of all the new accounts in August, or well, August is the month that we were simulating here, out of all the new accounts in August, how many churn? We get 26%. But this turns out not to be really what we were looking. We were interested in like the overall behavior of like new accounts within 30 days. And this doesn't give us that, because like some of the accounts that signed up at the start of the month, they would have had 30 days to churn, and those accounts that signed up at the end would have had just a few days. So the sort of cumulative risk these accounts are exposed to is different, and we're kind of mixing and matching this kind of apples and oranges here. And to kind of compare these at an equal footing, we should use something called time event analysis, time to event analysis, or also known as survival analysis. And what this means that instead of just focusing on whether the end event occurred, in this case, whether the customer churned, we instead look at the durations from start event to the end event, but we also include the cases where the event did not occur, but it just kind of went beyond our kind of horizon where we're looking at. So this kind of stuff is called censoring. And we see it also in this example data set we have. So all the blue lines are effectively censored because all we know about them is that they didn't churn before the end of our time period. We don't know what happens afterwards, but we should include them in our analysis as long as we have data for them. So we convert this data to the sort of duration count, and And we know the duration for each account. We know whether they churned or not. And we know whether they were censored or not. So using just these 3 pieces of information, now we can apply survival analysis. And the kind of classical approach here is to use Kaplan-Meier estimator. And if you can plug these numbers in there and crunch them a bit, you'll get this sort of nice curve out, which tells you the probability of an account churning by the given number of days. So we were interested in the first month of account activity. So in this case, we would look at the 30-day value of this curve. So we get around 46% here. So if you compare that what we got with the naive approach, it's considerably higher. So we would be really underestimating our churn if we just relied on the first approach. Okay, so we've established that we have a problem with early churn. Like there's a 46% chance that account churns within the first 30 days. So we should do something about it. Let's say we have some magical solution ready off the shelf. We plug it in, and like the next month, all the accounts are now going through a different onboarding process, and we wait for a month and see what happens. So after we do the calculations again, do the Kaplan-Meier estimator, we see that now the orange line is the second month, so it's considerably lower, and it kind of shows that, okay, our mitigation efforts are paid off. Another useful thing that we get from survival analysis is the so-called hazard function. And in this case, it's equivalent to showing us like what is the risk of churning on a given day. And if you remember in the beginning, we said that as 2% probability of churning every day. And we're able to extract that from this data using survival analysis. And we also see that for the second month, when we deployed our fix, we saw that the risk of churning had dropped to 1%. So that's pretty neat to get out of this analysis. The second type of thing I want to look at is something called product activation. So that's when we have a new account signing up, and we're interested in when they start using a certain feature in our product. For example, like if you sign up to YouTube, how long does it take for you to start uploading your first video? So it's similar, but there's an added complication here because it's also possible that the account churns before it even gets to the event. So that's something we would have to take into account in our analysis. And again, to kind of quantify this a bit more, I'm going to do a generate data set, again, 1,000 new accounts, the same churn probabilities, 2% at first and 1% later. But then throughout the 2 periods, like 2 months, we'll have a flat 5% probability of the account using this product feature we're interested in, or also known as activating. And what we want to understand is, can we estimate the activation probability even when all of these churn changes are going on? So if we just use the first approach, just like, start event, end event, we'll actually end up with something that we are not expecting, which would mislead us if we didn't know that the activation rate is constant over time. In this case, we would see that, well, the September activation rate is higher than August. It's kind of depending on the churn rate then. And also on the right, we see that the activation probability seems to be going down over time, which also we didn't specify. We had a flat activation rate overall. This problem occurs because we're not taking churn into account here. We're just ignoring the effect of churn on this. But if we do take churn into account in our calculations, we actually are able to obtain the results that we would like to see. We have the activation probability for both months is the same, regardless of the churn behavior. And we're also able to retrieve the activation probability, the flat one. It's getting a bit more, there's more variance at the end there because there's fewer days at the end. But otherwise, it's flat around 5%. And yeah, those are the 2 examples I wanted to cover quickly. I think it shows pretty nicely how you can employ survival analysis to analyze customer data. And this was done using the Lifelines library. It's open source or Python, and you can do a lot more fancy things with it, like regression models to figure out which features contribute to survival and how they do that, and a bunch of other stuff. And it has really good documentation, very nice tutorials, so really recommend you checking it out. And yeah, coincidentally, yesterday there was a workshop done in PyData, which was about computational survival analysis. So if you want to kind of know what's kind of under the hood of all this, feel free to check out the recording. It was pretty neat. And that's all I have. So if anybody has any questions or like follow-ups, feel free to reach out to me, either by email or LinkedIn. And yeah, thank you for your attention and enjoy the rest of the session.
Thank you very much, Ardo. And it's actually very useful for me personally for my own use case. So thank you for the talk. I think we have the last talk for our lightning sessions with Jason. Do we have Jason?
Yep.
All right. Right. Whenever you're ready, Jason, you can start.
All right. Yeah, thanks. So thanks for coming to the talk. For the topic title is Improving Topic Model Interpretability Through Aggregation. My name is Jason Lee. Just by way of a quick introduction, I'm a staff software engineer at Flatiron Health. Project is independent of any work at Flatiron, and it's an independent project been doing over the last 3 or so years in conjunction with the University of Cincinnati Digital Library. And just a quick plug, Flatiron is hiring software engineers and data scientists. I posted on the job board, so please reach out if you have any interest or questions around that. All right, so the topic modeling primer, Banjo actually talked a little bit about this earlier, but just give a little bit more summary on topic modeling. It's an unsupervised learning method to find topic clusters in a document corpus. So for example, the algorithm will learn term topic document weights, allowing the certain late relationships based on the co-occurrence of those terms across documents to rise up. There are a lot of use cases in industry, but there are also certain drawbacks to the algorithm, sensitive to initial conditions, leading to topics not always being interpretable or reproducible. And this is sort of well described below quote. There's a fundamental instability in these algorithms, and different runs of the same algorithm can produce different outcomes. So then what did we do to try to make this better? Well, our approach was to aggregate topic models. So then for a given set of input documents for a certain corpus, aggregate recurring topics across runs. So what we did is run many PySpark LDA models, say around 50 per experiment, with different topic counts ranging from 50 to 400, that allowed consistent topics to bubble to the top. And it was a more natural way to get the number of topics in clusters. Generally, the number of topics is a parameter you need to input at the start for when generating the LDA model, and it allowed us to smooth out the terms, reduce some of the variability from the random initialization of the models. And the clusters were formed by aggregating topics using Jensen-Shannon pairwise distance and some network-based clustering heuristics. So just to dive into an example here. So this is from PubMed search for machine learning and artificial intelligence. There are about 30,000 documents there. And you see 2 example topics which are grouped into the aggregated healthcare innovation ethical cluster. But looking at the topic on the left, it's not immediately apparent that it is pertinent to healthcare. There's nothing related to healthcare or health in the top 10 terms here. But it's only when compared as the topic as a distribution with other topic runs across different models that it's clear that it's part of this latent theme of healthcare innovation and like ethics around machine learning. And yeah, so as I mentioned, this is for the machine learning AI docs in PubMed, but then we also created a UI to sort of to understand the model, and the color coded by confidence and what we call ubiquity across the models. For example, 90% of the models have the similar topic, or 75%, et cetera. But then how do we evaluate the models? How can we say that they are more interpretable? Well, we use coherence, which is a standard way to standard proxy for human interpretability. And in the table on the right, show on the top the ML AI documents from PubMed and the individual Spark LDA runs, where we are comparing sort of the 50 topic models. We ran 20 models for those, and the mean coherence across those was 0.493. The 200 topic models ran 12 runs of those, and the mean coherence was 0.499. But then the aggregated model, if you focus first on the part bolded in black, the aggregated model had a mean coherence of 0.596, and that yielded 115 topics or clusters. But then the bolded in red is for the models. The bolded in black are the ones where it appeared in greater than 10% of the models, but then the bolded in red is where it appeared in greater than 25% of the models. And that coherence at point is 0.657, so higher confidence, higher coherence on that. But then there's a trade-off was there's a lower number of clusters or topics, in this case 61, that were had greater than 25% of the models. We ran similar experiments for PubMed documents, which were published in Q4 of 2020. There are 400,000 documents there. And you can see likewise improved coherence with the aggregated model versus the individual LDA topic models. Just one point is for the ML AI model, we generated 3,600 topics across all the LDA runs, and about 1,000 of those were used in the final aggregated model. I mean, I guess the intuition here, and I guess we need to dig into this a bit more, is that 70% of the topics are noisy or inconsistent. Then to the next slide. So yeah, in order to generate these aggregated models, we need a lot of raw material, a lot of these topics. We initially tried GenSim, even with the distributed or multi-process version of GenSim, and that was still took a bit of time. But the PySpark implementation of LDA was very fast, even on a relatively small cluster of 2 to 3 R5 8X large machines on AWS. We're able to run for the 30,000 document corpus within a 50 topic model within a few minutes, 400 topic model within 10 minutes. So we had all the 50 topic LDA runs that we needed within a few hours. For the larger 400,000 document corpus, we were able to do it for 24 minutes to an hour, depending on the number of topics. And we had all the raw topic models we needed within a couple of days. And just to sort of illustrate the overall pipeline, the documents were ingested into Elasticsearch, and we did some pre-processing using SciSpacey, and then using PySpark, generated the models and computed the pairwise distances between the topics. And then post that, we used NetworkX to build a model, build a graph of the topics, and sklearn to refine these clusters using dbScan, and finally GenSim to score the models, the coherence scores for the models. And we did a grid search phase to determine the best parameters for the final aggregated model cluster. And yeah, the work this yielded a paper on the Core 19 data set that was published in the Harvard Data Science Review in conjunction with the University of Cincinnati Digital Library. One takeaway was there was a 71% correspondence to human annotated labels. And you can see how this could potentially streamline, expedite human annotation using some of these high confidence clusters. And a link to the model is provided below, which I'll share in the slides. And yeah, thank you for listening.
Thanks a lot, Jason, and congratulations on publishing the paper. Are you going to post, like for people, what can they find the link to?
I can post the slides in Slack, I guess.
Okay, yeah, great. With that, we conclude our lightning talks for today. Thank you everyone for joining us. And I hope everyone enjoyed the talks. You can find the recordings on the website. We have recorded all the talks. You can revisit or approach the people that gave the talks. And with that, thank you so much and have a great evening. All right.